There you go. I'm starting to record now. All right. Welcome to Game Engines. Or no, wait, this is GPU. This is Vulkan Graphics. Very cool. All right. So if you install Vulkan off their webpage, it should show up here in your C drive under Vulkan SDK. The version number will be right in here. And today you're going to need to know the version number that you installed. That will alter things. I'll show you later on today what that's about. You can go in here, and then this is all the stuff that they will install. There's a lot of stuff going on in here. You know, Darlene, there's so many new features. Every time they come up with something here, they've got new features I honestly have never even heard of. So I installed everything I could that one time. I didn't do all the extra debugging tools. I didn't put those in because we should learn how to debug this thing kind of the hard way, so you get a feeling of what Vulkan is all about. So I installed it on the computer at Humber. I installed everything, and it seemed to work fine. Nahid, no, you don't have to use my engine. What I've done on my stuff here. Let me bring that window back up. On this one here, I've taken a basic kind of a framework. It's not the stuff we did in Engine 4 class. So this is stripped back, back to the beginning. So yes, it has memory leaks and things in it that we uncovered in Engine 4 class. I stripped it back here, and I'm just trying to set up an environment where we can set up the Vulkan renderer. And today I'm just going to take you on a tour of the Vulkan renderer. I almost slipped and said I'm going to take you on a quick tour of the Vulkan renderer. There's no such thing as quick tour of anything in Vulkan. So it's going to be a long-winded tour of it, but I would recommend that you just start there. Just start with my stuff, and then later we can move it into a better engine or into a better framework if you want. At the end of today, you'll see why, I'm sure, and probably agree with me. I'm seeing little messages pop up on the screen, but I don't see them scrolling over here.
Oh yeah, those are just like for like the chat on the
Yeah,
meeting
I'm
thing.
looking at the chat, and it wasn't the chat wasn't scrolling down, so I would see that you just typed in something, but it didn't show up on the computer.
Yeah, it's a weird game thing. I don't know if I can turn. I should see if I can turn that off.
Yeah, I'll tell you what, I'll get used to this. It can't be that bad.
We'll see about
If
that.
administrators can figure this out, I know I can figure this out.
Hell yeah, that's the spirit.
But they don't have anything to do all day except figure things like this out. That's what
Right.
I think that's the role of administration, is to have meetings and discuss things. Not actually get anything done, but just discuss it all. Okay. Yeah, I got that. Okay. What did Lucas just say? Like what? I don't know what they talk about. I've been to some of those meetings. I never know what they talk about.
I've stopped going to those meetings now. Now I'm not coordinator.
It's amazing. As soon as you stopped being a coordinator, hair started growing out of your face. It's cool.
Oh, I can relax.
I like this humor. I like this one a lot. Okay, is everybody good?
I'm having just a slight problem.
Of course. What?
It's very slight. So when I open up the project, it's asking me should I retarget to the latest version of Windows SDK.
Yes, you want to do that. So,
Excellent.
we're at a crossroads here where some of you will have Visual Studio 2019, and some of you will have Visual Studio 22. And so I compiled this version on Visual Studio 19 because it'll just ask you to retarget. Whereas if I compile it on 22, then you have to manually go in and change the version. It'll just tell you that you haven't got the right version and you're all fouled up. And you'll have to go into properties and then backtrack. And that was more effort than to push it forward. So I went ahead and compiled it on 2019. Hopefully we'll all be on 2022, especially when it comes time to grade these things. Then I have to update or download or whatever. So does that fix your problem? No, Lucas, you don't have to go to 22. I can cope. I can cope. I don't see anything new in 22 that is different. I don't see anything. But then we don't use. What'd you find?
Oh yeah, one thing new is this GitHub Copilot AI,
Oh yeah.
which is it really gets in your way more than helping.
And the rest is just quality of life stuff.
And honestly, I've got this up right now, and I don't even know what version I'm running. I imagine I'm probably on 19 as well.
Yep. Old logo still on the top left.
Yeah. Yep.
Yeah.
Yeah, it is. It is. It's 19. Is there a way to look at who all is logged in? Like the whole list? Let me rephrase. Is Joshua out there?
Yes, there is a way. If you click on people,
There
it
you
should
go.
say who's here.
Oh, look at there. My gosh, everybody.
Yeah, good turnout.
Ooh, people.
People from yesterday as well.
I don't see Joshua. You were helping him with the with his bug yesterday, weren't you, Umer?
Oh yes, yes.
Yes.
You didn't have the Vulkan DLL file.
Yeah, and this is a little bit of stuff that I put into the into our program that might help find out what's going on with him. And look at me using a pragma. How about that, huh? And so this particular pragma is pretty cool. This one, oh wait, how do I get back to chat so I can see what you're all saying? Look at me go. I'm getting it. Okay. This particular pragma will disable the warning, warning number 4996, which will prevent me from using the standard library get environment variable, because it's returning back a pointer to this thing, and it does, and Microsoft doesn't like it. But what that'll do, that'll print out what your environmental variable path is equal to, and that'll write it to the console. Now I've commented it out because it's a really big long string that's going to come out, and you do not delete. That's the worry that Microsoft has, is you might delete that pointer thinking that it's a memory leak, and it's not. It's a pointer to a copy of that string, so you do not delete it, and it returns the environmental path, and the environmental path is how it's going to locate DLLs. So the DLLs on any particular run are going to be generated by the environment variable path, and we can go see if his path is messed up. and I couldn't remember it yesterday because it was my first day back in Vulkan after a year. And I remember that there are some other software programs that you can load onto the machine that will reorganize your path variable and foul it up. Not everybody behaves correctly. And since everybody needs to use the path variable, if some rogue piece of software messes with it, then we can get that fouled up. But we can always go in and we retweak it and fix it. So anyway, that's hopefully the patch that'll get Joshua back up and running. Okay, is everybody is everybody cool? Has everybody got the Vulkan installed? And a new version of Game Dev. Oops, we don't want that. Lucas, cool, good for you. Okay. Naeed, go for it. Hey, you're going to do it on Unix again? You're doing this on Linux? Naeed's a monster, Umer. He's a monster.
Oh, I love it.
2,000 lines. That's it? Oh, that's nothing for Vulkan. Oh, fantastic. Okay, let's see what we got. Okay, so let's go and take a look here real quick. If we go over to the Vulkan SDK on the C drive, go into whatever version it had, and then in here there should be a binary file. This is going to be bin32, which is 32-bit version. That'll be the 64-bit version. Okay, and there's a whole ton of interesting stuff in here that we'll come back to later today maybe. Okay. But one thing that we can check real quick here is, let's see if it's in here. There it is, vkcube.exe. And if you click on that guy, you should get a Vulkan cube flying around. Sargis, that might be a bit of a worry. If it only has bin in it, that might be 64-bit, and we may have to go tweak your Visual Studio. The framework that I gave you, the Visual Studio framework I have, is all set up to operate on 32-bit, not 64-bit. So if you guys see the cube and that cube is up and rotating like that, it means your graphics card is Vulkan compatible and that Vulkan can find it. This does not mean that we can find it, but it does mean that it's findable. So if that runs, we're in good shape. Okay. Tyler, I think I saw you. Are you out there? Sergis, that's...
Oh, I just noticed.
Yeah.
Sorry. Yeah, I just noticed. Yeah, if I downloaded the newest Vulkan,
right,
and the spinny cube is in the bin folder.
Okay.
It's not in the bin 32 one.
Okay.
So Darlene, yeah, have a look in bin instead. So the bin 32. That's where it is in the new version of the SDK. Looks great.
Yep.
On this laptop anyway.
The honest truth here is I'm scared to remove the old version and install the new version just because everything else has failed this semester on me, and I don't need one more variable. So maybe this weekend I'll undo it and go to your guys' version of it when I have more time. I would imagine not, Candide. I would imagine it's going to be internally limited by the whatever framework they're using for the speed rate. Lucas, I don't think you have to. If you've already got Vulkan on board and it's spinning, I would just leave it for today anyway. Okay, so enough of this stuff. If everyone's got that kind of stuff going, let's get over to the framework and let's get busy. Let's go learn some Vulkan code. Okay, let me get rid of main. And what I've set up for you here is pretty much the same setup as you've seen many times before here. Let's get rid of math. You don't have to see that one. And I've got some renderers here. So I've got an OpenGL renderer and a Vulkan renderer.h. And the OpenGL one is not even working. There's nothing in it. It's just a placeholder, and I'll show you how that links up another day. And so what we've got down here is scene 0. And hopefully this just makes your life easier to understand. And over here in scene 0, I'm going to go in. I'm going to make a camera. There's the destructor that will delete the camera. There is no camera. And right in here, if I detect that I'm trying to use the renderer as Vulkan renderer, then I'm going to set up the camera for some perspective and things like this. And then down here at the bottom, I'm just going to render. And we'll get through how all this stuff works. And we'll do much of that today. Okay. So let's give this a try, everyone. Go over and somebody actually said hitting the green button was press play, and that just killed me. We're programmers. We don't press play. Gamers.
Oh, that was.
Was that you?
That was me. That was me.
Funny. Okay. And if all this is working, Mario should pop up. Hey. Tanner, go up and make sure that you're on. Let's see here. You've got to be in a. Let's see here. Right up here, you're going to have to make sure that you're not on a 64-bit build, that you're on the x86 build. Unless you guys all want to use 64-bit libraries. And if you want to do that, then I can help you out next week on it. And if you, Tanner, if you're on the 64-bit build and you're still getting include errors, then go over to your C drive. Let's see if we can go find my C drive again. That's it. Here's the C drive. And here. Hey, thank you. I got a compliment. Umer, I got a compliment. Somebody likes my code. So the Vulkan is in here, but don't forget, you still have to have game dev. And yesterday, a couple folks, when they installed game dev on the C drive in here, they when they unzipped the package, it made a subdirectory called game dev, and then inside it made another game dev. And the path here is just these things. And you can see in the latest version here, I'm trying to get it so that we can put Vulkan inside here, and we don't have to actually do the install anymore. But it does come with a lot of other features that are kind of handy to have. And I don't want to beat up on Vulkan too much. So see if that'll work, Tanner. Lucas, good for you. Tanner, what's going on? So, can you copy and paste into the comment what the error is or what it's saying? Is it just saying it can't find the path? Ah, good. Okay, is anybody messed up? Does everybody have Mario floating around? Okay, Brian. Tyler, did you do the cube and see if the cube is spinning?
Yeah, I tried the cube and it wouldn't work on me. It said, what does it say here? BK enumerate physical devices, report as 0, accessible devices.
Uh,
And it
Would,
said, do you have a compatible Vulkan installable client driver, ICD, installed?
yeah, okay.
I'm
Boy,
just looking it up online, seeing if I
yeah.
can find any information.
I hope you don't live far away from Humber. We may have to do this face to face. I don't know what that is compatible with the error you had yesterday. But I mean, at least it's consistent, so it's not our code.
Right, okay. Yeah, no, I'm like, I don't know, 40 minutes from Humber. It's not too far.
Okay, so we'll figure out something here. I'll stay in touch with you by email.
Cool, cool. Thank you. I'll just keep looking online, see if I figure it out, I'll let you know.
Yeah, please, because that's what I'm going to be doing. Trying to figure it out. You just wrecked my weekend.
Apologies.
Don't. I don't know about Umer, but that's where I get paid. I don't know if they pay him. I think he may be voluntary. He enjoys this too much. Look at this maths. All right. Let's go take a look at what's going on inside this program here. So I'm back into scene 0 here for a second, and as you might guess, let's see here. On create, setting up some windowing things in here, setting up the aspect ratio and getting the perspective matrix all set up. And then down here on update, I'm just doing that real cheesy thing with the static. I think I showed that to you in OpenGL class. I'm not proud, but it works. So we're spinning around the y-axis, and I know Lucas gets a real kick out of making it go crazy fast. So have a good time, Lucas. So change that to 190 and it'll really fly. Excuse me. All right, gang, if everyone's pretty much working properly here, let's dive into Vulkan. What do you say? It's only been coming up on an hour that we've been messing around with this. Very good, Lucas. Okay, so for the sake of this class, what I've done here is I've created way over here a Vulkan renderer.cpp file. And if you were to open up that file, first off, I guess I should have done this yesterday in class. Let's get rid of that breakpoint and go all the way down here to the bottom of this file. And the first thing I wanted to alert you to is this is going to be a big day here. This thing is 1,400 lines long. So this is 1,400 something lines of Vulkan code. And this is the basics of getting Mario spinning. And these aren't even the support routines. This is just the base code. So Vulkan is dragged this way in that it takes an awful lot of code to get it all put together, to get it up and running in the first place. Now the reason for this is based on a thing called a driver. Have you guys all heard of drivers? I mentioned this yesterday in class, so this is old news for Candide. But the idea here is that there is a thing called a driver, which is a piece of software that literally links the hardware and the software together. Now, I've kind of lied to you over the past couple of years, and not really evilly lied to you, but I say that when we're in C++, we can actually really kind of talk to the hardware, and that is true. So it's not really a lie, but what's really true is we are talking directly to the hardware via the driver, though. So we're speaking to the driver, which is actually talking to the actual hardware when it comes to graphic stuff. Now in OpenGL, you might have thought when I showed you guys OpenGL that OpenGL is a real drag, and it's, boy, you got to write so much code to get things to happen. Wait till you get into Vulkan. Boy, that's going to change, because the OpenGL driver is what I refer to as a thick driver, meaning that there's a lot of code in it. There's a lot of stuff that the OpenGL driver does, and all this stuff is for the most part, it initializes the hardware. You got to keep in mind while we're playing around with Vulkan that we're really treading into an interesting world. We got the CPU, and we programmers are really good at working on the CPU. What is really different about this is there's a whole nother chunk of hardware out there, and that's your GPU. And somehow we're going to be controlling the GPU through the CPU, but then we want to leave the GPU running wild. I want the GPU to fly as fast as it can without any kind of hand-holding from the CPU, at least as minimum as possible. And that's sort of the task at hand, and that's where Vulkan came from. It's you guys, you gamers, that said, hey, we want even more performance, better performance. How do we make it run faster than even OpenGL can go? And the engineers come back with the idea, well, if we made the driver really thin so that the driver doesn't do anything for you, there's no error detection, there's no anything in it. If we just let the machine run wild, it can go a lot faster. Thus is Vulkan. So Vulkan doesn't have a lot of error detection, and Tyler and I are going to fight that battle because it doesn't tell you what's wrong. It just doesn't work. So let's go up and take a tour of the Vulkan system here as I've got it set up for you. So it's way up here at the top. This semester, what we'll be messing with mostly is taking this particular file and reorganizing it and rewriting it and fixing up little bits of stuff. Now, periodically, I'll tell you, here's a subroutine. Don't touch it. Just don't touch it. When you turn a computer on, when you turn any computer on, it comes up in an unknown state. You never know what the little flip-flops, these are the low-level circuitry that's inside the machine. You don't always know what state they're going to be in. Is it a 1? Is it a 0? You don't always know. Machines don't always boot up real clean. And same thing with the hardware, with the graphics hardware. You don't really know what's going on and what state the machine's going to be in. So what we have to do, unfortunately, is we have to initialize everything. Even things we're not touching, we have to initialize. And that's what a lot of this code is. So it's really not hard to deal with. You write it. You're only going to write it once, and then you never bother writing it again. And that'll initialize things. And I'll just take you on a tour of what things we can manipulate and which things we should just leave alone. Now, you'll notice in the code that I've given you here, I don't have any comments. And I'm doing that intentionally. I'd like you to put comments on here. So as I'm starting to describe how things work, put comments in there that you'll understand. Because if I can't explain it to you verbally and you don't get it, and my comment is in there, it's probably going to be the same style that I just said that. And so you still won't understand it. So if you finally understand what I'm doing, put your own comments in here so you'll remember. Trust me, you're really going to want to put a lot of comments in this stuff because you'll forget quickly what all's going on here. Okay? All right, so let's dive in. Here's the, let's see here. Let's go up to the top. here's the constructor for this thing. And notice up here in the constructor, all I've done is there's a bunch of member variables here, and I've just initialized them mostly just to be null or 0 to start off with. A format that you may not have been familiar with really is this in C++. Swap chain extent is going to be the name of a kind of a structure. And by using open, close, curly Q brace like that, it takes anything that's inside that structure and zeros it. So it makes sure that everything inside here is clean. So don't let that nomenclature fool you. That just clears everything out. So I've done nothing here but just initialize some variables. That's all we're doing. No big deal. I'm not going to allocate anything or deallocate anything in here, so the destructor is just fine. That works the way you would expect. All right. Now here I've got a create window. This is the pretty much first and only time we're really going to be using SDL very much. Here's the SDL init, and you can pass it SDL init video, or you can pass it SDL init all. I would recommend that you don't do init all. That turns on a whole bunch of SDL subsystems, and on some computers that really it slows the load time down. So as it's initializing all the subsystems, your computer freezes for a moment, like a real moment, like maybe a minute, and then it just locks up, and then eventually it comes back online. So don't fire them all up. Just use video today. Maybe in the engines class we might want to add init audio or something like that, so we can do other things. But I'll help you out with that in the other class. Okay, and then here, SDL create window. This works just like we have before. So what I've got here is a string, and I'm going to convert the string to a seek a character array, because SDL create window is going to want a character array, not a string. This is how you do that. I'm going to have the window centered. Okay, the window is going to be centered, and the position is going to be centered. We're going to give it some width and height that I've already predetermined. And the only thing that I need to alert you to here is this one. When you turn the SDL window on, you're going to have to tell SDL that you're going to be doing a Vulkan version of this. All right, and so I've set that one up for you here. This is going to make it so that the window is resizable. That's going to cause us a lot of headaches later on. It's going to be great fun. When you resize the window, it's going to blow up everything in Vulkan. It'll be great. It'll be great. Lucas, you're going to love it. Okay, so that was the end of create window. And then just to continue with my normal philosophy of things, I have an on create here, and the on create calls init Vulkan. I could have taken all the stuff that's in init Vulkan and just put it in here on create, but I'm going to call it init Vulkan for today. We can rearrange this stuff as time goes on in the class. Let's go take a look at what init Vulkan does. So if I were you guys, I'd sit back and enjoy the ride here, because it's going to be kind of a long discussion of what things do. Be sure just to type in some comments. There's no coding today. There's just going to be, let me show you what's going on and what all has to happen in the Vulkan renderer to get these things to work. And it is, in fact, horrifying. Brian, that's exactly how I completely forgot that you were having that problem. That's what I was going to suggest. And Brian, what you might want to do, send me an email. Go back to main. Let me go over to main. Oh, where's main? Here it is. So Brian, why don't you go over to main, uncomment this code, run it, and then send me an email with what this thing prints out, so I can look at what's your path variable. So putting all of the DLLs into your debug folder, that should not have to happen. I've loaded up the properties menu so that it points towards game dev. But if you've had to move everything into your debug, I think that means your environmental variable has been butchered somehow. So do that, send me an email later on. But congratulations for getting that fixed. Okay, let's go look at init Vulkan. Here we go. So I'm going to go over to here and say, let's go to the definition. This is what it takes to Load up Vulkan to initialize Vulkan. All these commands. It's not too many, I don't think. Do you think? Let's go look them up. Let's go look at each one individually today. Well, most of them today. And I'll show you what's all going on. So this is where I'd like you to put your original comments in here. Create instance. Let's go take a look, see what create instance is up to. Okay. Vulkan renderer, create instance. Okay, first thing it's going to do is it's going to enable validation layers and check to see that you have validation layer support. Stop right there. I got to explain validation layers. All right, in OpenGL, if there's a problem, the driver responds back with, hey, something's wrong. Let me give you some debugging help and all that. Well, that takes time, and that takes CPU time and GPU time. And so the writers of Vulkan, by the way, footnote, Vulkan was written by the people at AMD graphic, what do you call that stuff? Graphic card makers or chip makers. They're the ones that invented this sucker, so we can blame them if it's miserable. And then they gave it to the Kronos group. And the Kronos group is the same group that operates OpenGL. So they gave it to them to support everybody. And their motivation, of course, is to sell more graphic cards. So that's why they don't want to take care of it. Let Kronos do it. Okay, so the idea here is there is no runtime debugging in Vulkan. And what they've done is they've separated it out, and they call the runtime error validation stuff, they call these things validation layers. And we can turn on and off the validation layers. You'll get much better performance if you turn them off. We want them on, but the crazy thing is you don't always even know if you have ability to turn them on. So there are so many different manufacturers of graphic cards. So Intel, NVIDIA, and AMD, just a few. All these things, and then there's 100 different versions of graphic cards from each one of these companies. So who knows what it's going to do. And this is going to be something you'll see. It's a common theme throughout this entire initialization process, is we're going to have to crawl through the hardware that you have and go find out what's going on with your particular hardware. Okay? So step one, do you have validation layer support in the first place? And that's a function that we wrote, and to go check out to see if you even have it. If you don't have it, then I'm going to throw a runtime exception. So if you see Mario, you now know you have validation layers. Excuse me, man, I've got a frog in my throat today. I wonder where that expression came from, frog in your throat. That would be gross. Okay. Now we're going to see this kind of, this next chunk of code here. We're going to see this style of code all over the place in here. So let me explain just from a C++ point of view what this is all about. All right. VK application info, as you see, because I put the cursor on here, is a structure. All right. Now, if you recall from earlier C++ classes with me, structures and classes are kind of like each other. A structure, all the member variables inside a structure are necessarily public unless you tell them otherwise. And in fact, in the old style of C programming, which is what actually Vulkan is written in, not C++, it's actually written in C, the structures don't carry any subroutines in them. So there's no methods, no functions, no subroutines, none of that stuff. So these are just packets of data. And right down here, you can see how that would work, right? So app info, this is the name of the structure. And at app info dot, we're using the dot notation because this thing is on the stack. All right, now here again, I'm using whoops, that was a boo-boo. Thanks, Microsoft. This notation right here with the open close curly Q braces is going to make sure that everything inside the structure is 0. If you want everything to go away and break and blow up on you, remove all the open close curly Q braces. That'll work. And I'm very familiar with that because I've done that, and it don't Just don't. All right. So the reason I'm doing it that way is that there are a lot of fields inside this structure. There are a lot of fields in here, and I may only set a few of them to be non-zero. So this will make sure that everything inside of it is 0 first, and then we'll set these things to be something other than 0 if they need to be. So let's dive in and show you what the first thing is. The first one has to be set for this. It's its S type. That stands for structure type. So these structures, when you're passing the information into the GPU, remember at the very lowest level now, because there is no driver to help me out, when I'm passing this information into the CPU, or sorry, the GPU, it's just going to be little bits of ones and zeros. So how is the computer supposed to know, or how is the GPU supposed to know what's going on, what information is being sent to it? So the way it's going to do that is it's going to look right here at the S type. Now that's going to be a known variable, and it's only going to contain basically an unsigned integer. And it's going to be an unsigned integer set to the value of sk, oh, you're going to love this, guys. sk underscore structure underscore type underscore application underscore info. Oh, that's a mouthful. And what that's saying is that the data that's in this particular structure is of this type. And I know it's extremely verbose writing it out this way. Look what it comes out to. When you look at the enumeration, it comes out to be 0. So this is the first one, application information structure. So that's enumerated to be a 0. So you pass 0 in and it knows, oh, this is tell me about your application. And it's hello triangle. That's where I got the idea originally, but I thought a triangle would just kill you guys. We spend this much time and all you get is a triangle? No way. No way. Hang on a second. I've stopped my, oh, come on. There we go. Okay. So this stuff is really not very important. Really, this doesn't even show up on anything, but we're going to set what the application is. This is a little defined statement here that allows you to make the major, minor, and whatever for your version numbers. You don't really need anything. I just put in no engine. And so there's just a bunch of information that you're going to need. Okay, well, you don't even really need it. You can actually set all that to be nothing and the program works fine. I have no idea why they've got it in here, but they do. So let's just do it right. Okay, the next structure I need to fill out is a VK instant create info. Ooh, what's that about? This is about creating the instance. And to create the instance, you got to tell it what type of structure is it. It's a VK structure type instance create info structure. Oh, and what does it enumerate to? You want to bet it's like 1? It's a type 1 structure. Oh, and what does it hold in it? This part kills me. I love it. It holds a pointer to the application info structure. How are you supposed to know how to do this? Because I'm going to write it for you. You use it. Don't ever touch it. And you can change the name of it from Hello Triangle to Hello Mario if you want. But otherwise, don't mess with it. Please. Okay. Then there are some things called extensions. These are features that the graphic card may or may not have. And I'm going to get all the required extensions in order to get this program up and going. And we'll look at this code maybe some other day, or you can go look at it over the weekend and don't tell me about it. You can go see what that's up to. We're going to be doing this a lot. We have to go in and query the gizmo that you're playing with, the GPU that you have, and ask it about all kinds of things. We're also going to have to ask the software if it knows what's going on. So we have a lot of questions to ask of the software, and later on we'll be asking a lot of questions of the hardware to find out what's going on. For the most part, this stuff is not something you're to mess with, so you might want to put a comment on here, don't screw with this stuff, please. So if validation layers are installed and everything is working, then we need a way of actually sending messages back and forth so you can see them on the screen when this is going on. And that's what this business is all about in here. Here's yet another structure, VK debug utilities message create info extensions. Don't screw with this. Just leave it alone. Don't touch it. Okay, so that pretty much sets up all the information. Now that you've got all this information and all these things are all pointing into the create info structure, here's the real call, and that's it. But I had to set up all those structures and load all the data into those structures so that the create info is completely filled out, then call VK create instance, pass it a pointer to that structure and an instance that we, and then we'll get back the instance from this thing. That's what this is going to be. So now I will have an instance of Vulkan. And an instance just means everything is set up, everything's ready to go. Now we just need to do the hard part. Okay? All right. Let's go back. And that was create instance. So this is just going to go create an instance. So give me a comment up here someplace saying that this creates an instance of Vulkan. Don't screw with it. Okay, the next one here is set up debug messenger. So we asked if we had validation layers, and in order to set up the debug messenger, we first have to ask, do you have a debug messenger? We work that out in create instance. So now we're in, we can go set up the messenger. There's not a lot of interesting stuff going on in there, so I think I'll just skip it for today if you're okay with that. It just sets up the ability to send out error messages so that you can see them, assuming you've got the validation layers. All right, now here's a little handshake that we have to do between SDL and Vulkan to create a surface to draw on. If you recall, SDL likes to think of windows as being surfaces, and Vulkan likes to think of things as frame buffers. And so we're going to kind of blend that out a little bit here by saying SDL Vulkan create surface. And so you notice it's an SDL and Vulkan call, and this was located inside SDL. If you're going to use another windowing package like, what is that one? FLDW, I forget what it's called, Umer. But I think you're muted.
Oh, yes, you're right. I've got so many windows open.
Yeah, I know.
Yeah, I think you're right. GFLW?
It's something like that. There's some other ones. I'm not claiming that I love SDL by any means. I'm pretty much agnostic about SDL. I don't care. GLFW. Thank you, Nahid. Thank you. The only reason I kind of like working with SDL for you guys is that SDL also has image libraries in it. It has audio libraries in it. It has network libraries in it. And so it's a very complete package. If you use GLFW, it's a lovely windowing package, but it doesn't have image libraries and things like that. So then you have to get another third-party toolkit in there. If you're so inclined, have a good day. It just makes your life more miserable. So I tweak this one back to go to SDL. Just makes life easier. And Vulkan's bad enough without having to fight other problems. Trust me. Let's go down here and pick physical device. Let's go take a look at this one. I'm going to go take a look at the code. Let's go to definition. Okay. I'm going to get kind of hardcore from now on defining variable types. So I'm using a uint32_t. It turns out that it's a type def of truly an unsigned integer. And we have been doing this in C and C++ for a long time, using a thing called a type def. It means type definition. And what I want to do is I want to make sure that what I'm passing to the machine is exactly what it needs. There is no interface. There is no driver, or a very, very thin driver. So if I was to send it a 64-bit int, or a 64-bit integer, and it's expecting a 32-bit integer, it's not going to complain. It's just going to read it wrong and die. And you will never know what's going on. So I'm going to have to be a little uptight about making sure, no, it's an unsigned 32-bit integer for counting things. That's what the _t means. So it's an unsigned 32-bit integer, damn it, okay? And I'll just be writing those out. So if it looks like I'm being fancy for fancy's sake, no, you got to be really cautious, because when you send this information over, if it's slightly out of whack, it's just going to blow up and you'll have no clue why. All right, so I'm going to initialize this variable to be 0 at first, and then down here, this is going to be wild. Check it out. I'm going to call it twice. VK enumerate physical devices. To do that, I have to pass it the instance, which we created earlier. This is the instance of Vulkan. So I'm passing it the instance that we've got. I'm going to pass it here, ampersand device count. I'm passing it a pointer to that unsigned 32-bit integer. All right, as soon as we're done with this particular subroutine here, I think we'll take a break because my voice is falling apart. It's day one. Come on, I've had summer off. I haven't had to talk this much in a long time. Okay, I'm passing it a pointer. Ampersand device is going to get the address of the device count and pass it down to this thing. And then VK enumerate physical devices is going to go down and look at how many graphic cards do you have and load up the number of graphic cards you've got, put it into device count. Okay, the null pointer says, don't tell me about the devices, just count them. Don't tell me about them. And then down here, what I'm going to do is I'm going to count or do a quick test. If the device count is equal to 0, well, then you don't have a GPU that I can recognize. So I'm going to throw an exception at you saying, I don't see any GPUs down there that have Vulkan support, at least ones that we can identify, that Vulkan's instance can identify as a GPU. So we'll throw that back down at you and die there. Okay, next I'm going to come down here, standard library vector, and open angle bracket, close angle bracket, physical devices. This is a vector, standard library vector. And look at this, I'm going to call it the devices, but I'm going to pre-initialize this vector to be the number of devices you have. It's going to be that long. Now, odds are you've got one graphic card, so more than likely this is just going to be one. But Vulkan this is the most powerful graphics language we've got going right now on the planet. And so if you were working for Pixar or somebody or other, and you had a big giant render farm and you had a $1 million computer with 80 graphic cards in it, well, then you would need to know all this stuff. And Vulkan, of course, supports it. Of course. So odds are we're just going to have one, but this is just how you set all this stuff up. And then here we go. I'm going to loop over all the devices. Well, kind of loop over all the devices. Let's say you've got 2. Just hypothetically, let's say you got 2. Don't put 2 in there. But if you had 2, I'm going to loop over this thing. So there should be 2 devices. There's a call down here that's going to go in and investigate in better detail the device that you have and decide if it's a suitable device for our application. If it is, I'm going to say that the physical device is equal to that device and then break out of here. So I'm going to take the first good graphic card you have. Okay, hopefully you've only got one, so this whole thing is just sort of silly. Don't mess with this stuff. Just leave it alone. Okay. If I eventually come back and find out that the physical device was a VK null handle, you're done. So I can't find a GPU that'll work. Bye. And so we'll throw an exception and get out of here. Okay. Hey, so the first thing we've had to do, let's go back and take a look at how far we've come already. I'm going to have to initialize an instance of it, set up some debugging stuff, and then pick the physical device. That's all we had to do so far. Wow. Okay, well, my throat's tired, so I'm going to go grab a glass of water. What do you say we take 5 or something minutes here and go take a break? I'm sure nobody wants to listen to me. And let's hear.
Sounds good. Thanks, Scott.
Yes. To get that much up and going, that's incredible, isn't it? So let's jump into here. Let's go look at create logical device. So let's go to the definition, fly over to here. The idea of a logical device is we're going to be talking to an abstraction of the hardware, not really the hardware itself. So the first part was to go out and find the physical device, the actual piece of hardware that you're going to be communicating to. And now that we've got that, and I've stored the physical device in a member variable, I'm going to come down here now and create a logical device. Now the logical device has a whole bunch of stuff in it that we'll have to kind of cover later, but I'll give you kind of a rough idea of what's happening here. Here we're going to go in here and find these things called queues. And the queues are going to be doing all kinds of stuff. It's for queuing up things that we're going to want to do. Let me backtrack a little bit and try to explain what I mean by queues and what this is all about in terms of the performance of Vulkan. So in OpenGL, there's a much closer connection between the CPU and the GPU. In Vulkan, what we're trying to do as much as possible is break that connection. So I want the CPU to say things to the GPU and then just leave the GPU alone. Don't wait for it to signal back that I'm done. Just let it fly. Now think about it for a minute, and that should kind of make sense if you wanted to get ultimate performance of this. Let's go back, and if you remember OpenGL days, if we were drawing at 60 frames a second, that would mean that I'm calling render 60 times a second. And every time I called render, I had to go send it the projection matrix, the view matrix, the model matrix. I had to bind textures and all that kind of business. We had to do all that stuff in the render. And so I'm doing all that communication between the CPU and the GPU 60 times a second all the time. Now, if you're playing a video game, there's got to be some times when you're playing the game where you're thinking about what you're trying to do in the game, and you probably didn't touch anything for a second. And let's just leave it at a second, and let's just assume, don't complain about my frame rates here, but let's just assume you're running at 60 frames per second, and you've decided to think about it for a moment. And during that moment, let's say it's 1 second or 2 seconds, that's a lot of redrawing of the frame. The graphics hardware still wants to draw everything, but there's really no reason why the CPU needs to tell the GPU anything. Just draw it again, draw it again, draw it again. So if I'm going to cut the strings that hold those two guys together and just put everything into what we're going to later call them command buffers and different queues and things, and I'm going to set all that kind of stuff up as this is what the hardware is doing. Now, this is not really what the hardware is doing. This is the software that's in the hardware. You know, kind of a hard thing to try to describe. So that's what the logical device is going to be doing. We're going to be talking to this logical device and doing things with it. And in order to find out if you've got these things called queues, we have to find out, well, what kind of queues do you have on your hardware? Again, you'll see that a lot today, is that I don't know what you've even got on your physical device. So here, there's a function in here. This is not a Vulkan one. This is one that we write. That says, go find out what queue families do you have. So what do you have physically on your hard drive, or on your hardware? So I'm going to pass it the handle to the physical device. It's just a value that says this is the hardware we're talking about. And what queue families do you have? And we'll put them into here. Okay. Now down here, I'm going to create a vector and VK device queue create info. Hey, done that one before. Set. Do you remember what set does? Hey, there you go. Go look that one up. What does the standard template library do with the command set? I'm making a set 32-bit value there. Can anybody do that? You're not going to make me do it for you, are you? Not a peep out of you guys. Oh, come on. I guess I'll have to do it. mind-boggling, isn't it? So what we're doing here is I'm going to make this thing a 32-bit unsigned integer called unique Q families, and I'm going to go put in the Q family values, and I'm going to load them all into this uint down in here, and load that up. It's not doing anything. Just don't touch it. Don't mess with it. I just thought I'd throw that at you. Have a good day and go look at it. Oh, hey, go check out set. That'll blow your minds. What do you think, Indeed? Did you read it? I remember reading that the first time and just thinking, really? Really? You're just making my life that much more complicated? Wow.
It's a lot, yeah.
Yeah. Okay, so here's what we're going to do. And then we're going to go loop over the families here. So we're going to make this whole length of stuff. So this it's like an array. And we're going to go make the array of these Q families, loop over all of them, and build a structure each time for one of these things. And then we're going to take the structures that we're creating here. The type is going to be a VK structure type define Q create info structure. And then I'm going to put the actual Q family into it, set up some other values here, and then I'm going to store a pointer a pointer to, oh, come, just read it. I don't want to talk about it. This is killing me. This whole sucker here is a vector, and so we're going to take this info and push it back into here. Just don't touch this stuff. This is another one of those things. Don't mess with it. We're just loading up all the data, and you got to have all this stuff in here, but we're querying the hardware to find out what the hardware has, what hardware capabilities there are, and then now we're going to be telling the logical device, so the abstraction of the hardware, will be telling it what features it all has by setting up all these data structures. You'll see that in Vulkan, everything is a darn data structure. It just goes on and on and on. It's all just data. And remember I said earlier on in the first half of class, you don't know what state the machine is in. So it doesn't, when it first turns on, it's not in some clean, ready to go, I'm ready to operate state. Nope, it's not anywhere near that. It's just a muck. So we have to set up everything. And that's the real drag of Vulkan. The cool thing about Vulkan is once you've got everything set up and you don't touch it, everything works fine. You just have to go through 1,400 lines of code the first time. So anyway, we're going to be setting up, this is setting up the queues. And I love this one because I've honestly, as soon as I saw this and I thought, oh, I wonder what that does. And then I thought better of it. I thought, no, you know what? Don't touch it. I don't even want to know. So I honestly will tell you, I do not know what that does. And I don't really want to. Someday I may need it and then I'll look it up. Okay. So once again, we're setting up another structure here. Here's a VK device create info structure, and we'll be loading up all the data in it. And it will require device features, like does it have all this business in it? Sure hope so. So let's speed up a little bit here. Enabled validation layers. Again, this is debugging. So we want to turn some of that stuff on. So if I am using enable validation layers, then I'm going to want to set up these sorts of things. And there's really no option about this. If you go look at other tutorials that are out there, out on the internet someplace, you'll see that they're doing it exactly the way I'm doing it, because there really aren't many options for most of this stuff. It's just at some point somebody's got to do it, and that's us. VK create device. We're going to go create the logical device from the physical device, and this is where this is the action. This is the real stuff here. We're going to take the physical device. I'm going to pass it which device I'm talking about, and then down here create info. I'm getting the address of the create info structure that I have initialized up in here, and I'm going to pass it down to it. And then I'm over here, I'm going to pass it the device. Okay. So now I'm passing in its address so it can load up and put information then into the device. So now we can come here and get the VK get device Q tell it what device we're dealing with, what families we've got, and what graphic cues and all this, and away we fly. Check that out. Isn't that kind of crazy looking stuff? There's graphic families and present families. Oh, another day, please, Scott, another day. Okay. So that was the create logical device. So we now have got an abstraction of the physical hardware that we're dealing with. Let's come in and start mucking with that. Let's go create a swap chain. A swap chain. Holy smokes. I'll tell you what, let's go up here and try this. I remember doing this one time and it worked out really well. I think there's a Wikipedia page on it. Oh, it was something like it. There you go. Makes sense. You want me to explain? So it's the swap chain is a virtualized chunk of memory that is this is what we're going to be drawing onto. So we'll be drawing onto these things. You'll see that we've got lots of different of abstractions for all this stuff. Oh, Sargis found the X. No, that's it. That's it. Let's go back to the code. I just thought you'd like to see that where these words all come from. Do you remember that in OpenGL graphics that we set the whole thing to operate under double buffer mode? There was a single buffer mode and a double buffer mode. I hope you guys remember that. Now in the idea of a double buffer, that's pretty simple. Let me switch to this. Hey, I think you need to look at Scott for this one. If you're in double buffer mode, what it means is you've got two buffers. So I've got two areas of memory. I'm going to be drawing into here, or I'm going to be drawing into this hand. And the idea is I'm going to display one and I'm going to draw into the other one. Now, if I don't do this, if I'm in single buffer mode, what will happen is that you'll be able to see the image being formed depending on how fast your monitor is actually scanning along. So it'll look odd because so if you've got 10,000 triangles on this thing, you would actually see the triangles being formed, or you might be able to see it. What it ends up doing though is it gives a flicker to the whole thing. So the images form fast, but you get this flicker. The way we got around the flicker was to use two different chunks of memory. So what I'll do is I'll form the image in the one, and then I'll display the image on the monitor with the other one. All right, now in Vulkan talk, I would have two swap chains. That's the way we would speak of it. Okay, now of course this is Vulkan, so nothing is normal in Vulkan. So how many buffers do you want? I don't know, as many as you want. So in create swap chain, we can make all kinds of buffers. You can have triple buffer. And in fact, a lot of people like triple buffering now. So that means I'm going to display one, I'm going to write in one, and I'm going to have one in reserve. And then we'll flip through them as we see fit. We'll get into that one of these days coming up. But one of the first things you're going to have to do is write in here. Well, what does your hardware support? So does your hardware support swap chains? Well, I mean, it'll support swap chains, but how many chains, how big, what have you got? And so this is the code that's going to come through here and find out what you have and how many images. There's also going to be things like the format. So what format are you reading and writing into? Now think about this, because this is at a very, very low level that we're working in here. So we can't just, man, I miss OpenGL, because OpenGL just sets all this stuff up for you. But I need to know, think about this. If I'm going to be drawing a picture on a screen for you, I need to know exactly the dimensions of your window. I need to know if you're in RGB mode or RGBA mode. I need to know if you're single buffering, double buffering, triple buffering. I'm also going to have to know, as we'll see here in a moment, I need to know your Z depth too. As we go through all the calculations to draw Mario on the screen, You remember, we will calculate how deep in Z space everything is, and we have a depth buffer. We'll come up against that one here in just a moment. And I've got to allocate memory for that. In the GPU has no idea what we're talking about. So I'm going to be asking it for all kinds of information about what format are you able to use, what kind of color, look at this, what kind of color space are you dealing with, all kinds of other interesting stuff that really I shouldn't have even used the interesting. It's lovely stuff, but we don't have to play with it. Don't mess with this code, all right? Don't even do it. So what we're going to ask here is what kind of stuff do we have? Later on, I'm even going to show you we have to ask what kind of memory do you even have? We can't even do something as simple as just, hey, I want to store a number in here. Oh, no, you better ask me if it's okay. It's crazy. Okay. So we're going to create the swap chain down in here, and what a lot of this business is doing is that when the swap chain is ready to be changed, we're gonna call, well, what we called it in OpenGL was just swap buffers. It was just like a GL swap buffers or something like that. Down in here, we're going to have to find out whether or not the VK get swap chain images have been contaminated. Whoo, man, it's complicated stuff. And if the image gets resized, then we'll have to then have to go rebuild the swap chains. It looks like it's ugly. Remember, I told you, I hinted to you that I set the window so that the window is resizable. If you resize the window, everything that you've just done in terms of organizing the number of swap chains, the size of them, the amount of memory, and the Z depth have all now changed. All your memory requirements have changed by stretching out the window. And I think Tanner's got it completely right. OpenGL, oh, don't worry about it. I'll take care of it. And then Vulkan, do it yourself. You've got no option. So just changing the size of the window is going to be a drag, you'll see, coming up soon. But once we write it, we never have to write it again. Okay, just keep that in mind. Oh, and I forgot. You're welcome. You're welcome. I put all this on the code and gave it to you so you don't have to type it in. You should see what happened to the first years, the first time I taught this course. I think Umar was around. They died. They go, hey guys, I got a genius idea. We'll type it all in. And that really did not work out well. Okay. So that ends the swap chain business. Let's get back out of here. Good. So now I've got the swap chain done. So image views and things. Let's come back to that one in a little bit. Let's come right down here to the render pass. I just, before I burn you guys out, I'll skip a few of these just because I know you're going to get burned out and tired, and if I get too esoteric about everything, it'll all just be a waste of everybody's time. So let's go take a look at render pass and see what's up in this render pass. Let's go to the definition here. Hopefully now the code isn't looking as bad as it did when I first showed you guys all this stuff. Check this out. It's just a structure. Don't get stressed. It's just a structure. It's going to be called color attachment. And we need to find out from the swap chain what format we're doing, how many samples we're doing, how to clear, load, this is just telling you how to take care of everything. We never did cover stencils. At least I never covered stencils. It's a way of blocking out where you're writing and what you're drawing into. And so all I'm doing here is on the color side of things, this is working out what are we going to, what values do you need to initialize things. So no big deal, no big deal. Then the depth attachment. This is that Z depth business. And so I need to tell it a little bit about the depth. But is the depth going to be 24 bits, 32 bits? Is it going to be 64 bits? How big is that depth buffer going to be? I don't know. And we'll find out what your hardware has. So that's what all that initial stuff was all doing, was we had to go in there and find out, well, what do you got on board? What have you got on this particular graphics card? There's only 1,000 of them. And so once again, this is just setting up a structure. And so hopefully you guys are starting to just sort of chilling a little bit and you're looking at this code. Oh my gosh, what am I supposed to do with this? What you're supposed to do is look and smile and say, man, I'm sure glad Scott wrote this out for us. That's what you're supposed to be saying. Okay, and then at the very end, we're going to set up all of these structures, point the structures to each other, the subpasses and dependencies and all, oh my goodness, all of this crud. And then here's the workhorse. VK create render pass, and that'll create this thing by passing it all that information. And if it works, we get a VK success. If it doesn't work, I'm going to blow up and die. And I'm yet to ever have that thing fail. Sweet. It's getting easier, isn't it? I tell you, it's getting easier. So we've just created the render path or pass. The next one down here, create descriptor set layout. You know, without even going into it, I don't even need to go into it. Can you guess what's inside there? Whatever a descriptor set is, and we'll find out what that is. But in there, there's going to be a whole ton of structures, and I'm going to have to set up all the data for all the structures, point structures to structures to structures to structures. And then at the very end, okay, now we can go take a look. And then at the very end of it all, that's right, go to definition. I'm going to go create the descriptor set layout. And so all this is just setting up all the structures and all the data you're going to need. And we're out. Oh, it's getting a lot easier. This isn't so bad. See, I know I made it sound like you're going to die. No, you won't. There's just a lot of information, and you have to set up everything. If you leave everything zero, Vulkan is so good. It's so good. When things don't work right, the screen is blank. That's it. That's all you get. The screen is just blank, and you're going to come up to me and say, hey, I've got a bug. My screen is blank. And I'm just going to look at you baffled. I don't know. I have absolutely no idea what's wrong with it. I don't even know how to debug it. And that part's going to really suck. But if we build everything nice and slow, take our time here, it'll all work out great. All right, let's go down to this one. This is my favorite one here because this is where I am exposed once again as someone who tells you, what do you call it, a prevaricator. I have been telling you lies all this time. Let's go look at Create Graphics Pipeline. Okay, in the past, in OpenGL days, I was explaining to you kind of accurately that we have a graphics pipeline. Actually, the graphics card does not have a graphics pipeline. There's no such thing. Now, OpenGL driver creates a graphics pipeline. So there is a graphics pipeline. I didn't lie that way, but I made it sound like it was a shiny tube that we pour all the vertices into, and that there were little doors on the shiny tube, and we can put shaders into the little doors, and we can modify things as all this data is flying by. And I kind of made it sound that way. And spiritually, yeah, that works out fine. That's a good metaphor for what's going on. But the way it really works is this thing there is no graphics pipeline really. We have to build one. So we're going to have to go down here and create the graphics pipeline. All right, this one we are going to mess with. Not today, but we will be messing with this file. So this one you can label as messable. What do they call it? We should label it volatile. That's a C++ keyword. This is going to be a volatile routine. We can adjust it later. All right, so right in here, I've got a little routine that is going to go read the shaders. And we're still going to have vertex and fragment shaders. In fact, we can have tessellation shaders, geometry shaders, tessellation controllers, the whole thing, just like in OpenGL. In fact, these things are all going to be written in the GLSL language that I taught you. It's also going to be in the Microsoft shading language, which is H something SL. And it can read both of these things. Now, the bizarre part is that we're going to be having to load up this thing called an SPV file. And the SPV file is not readable. It is in bytecode. And so it's got to be pre-compiled. You're not going to love this part. In Vulkan, you don't just take the shader and then say, here's the name of the shader, and then we run the program, and then the program gets compiled. I mean, that's OpenGL. OpenGL will read your GLSL file, compile it, link it, bind it, do all that stuff with it, and then execute it. Wow, thanks OpenGL, that was wonderful. How do we do it here in Vulcanland? In Vulcanland, you have to go write out your GLSL file. Then independently, you have to go over and find a GLSL compiler. No, yeah. You got to go find the GLSL compiler. Let's go over to here. I'm going to go to my window here. I'm going to go to Vulkan in here. Let's just go to the one you guys have, which is bin. And right there, the GLSLC. This is the GLSL compiler. And you're going to have to get a command line out, a command prompt, and type in GLSLC, and then the name of the file you want to call it at the end, and all that. Oh, you're going to have to do this manually and actually type in commands? Yeah, I know. I thought about that for a minute, and I thought, you know what? I don't think my guys could do that. First off, I know you guys don't commonly work on command line things. You got to be, I don't even know if Umer's old enough to have worked on command lines. I know I am, but that's all we had in the dark days. But sitting in front of a command prompt is something that modern folks don't do. And I felt bad for you. So let me show you something you're going to have to modify if you want any of this stuff to work today. So let me just put this off to the side for a second and bring up another window. Oops. That's not the window I want. I want this window. There we go. And I'm going to want to go to desktop. And that's where I've got, no, that's not the one I'm working on. I am working on solid state. There we go. This is fall 22. There's Vulkan. Down here in the component framework, we have shaders. And here's all the shaders you guys have. And let's just real quick take a look at example 27. This is the one I'm using. The example 27 came out of the web page that I put on my website. There's a link to a Vulkan tutorial. There's several of them out there. I like this one. I don't like his code so much, but I like the descriptions. They're all pretty cool. And so I've called most of my functions the same as they've called theirs. So that is a really good reference. If any of the stuff I'm talking about right now doesn't make any sense, go to that reference and go look up any of the functions that we've looked at today, and you'll find them in there. I'm using the same nomenclature that guy did. This is what an example 27, so this is the 27th example off their GitHub page of a fragment shader. Let's go look at the vertex shader. And I'm going to open that up with, let's see here. How about TextPad? There you go. And what you'll see here is that it's just gobbledygook. So this is a binary file that you cannot look at. That's a drag. However, you know what you can look at is you can look at the original code. So here is what the original vertex shader is going to look like. And that looks like normal vertex shader stuff. It's maybe a little bit more verbose than you're used to. Again, thank you, OpenGL. I got away with a lot of stuff in the OpenGL class. I got away with a lot. So we didn't have to put in all of these layouts and all this. OpenGL driver did it for you. So we didn't have to say that we're at location 1, location 2, location whatever. We didn't have to say any of these things. You just do it, and then OpenGL driver figured it out. Vulkan's not going to figure that out for you. So we can't do that. All right, so what we're going to have to do is I'll teach you guys how to work with the fragment shaders and the vertex shaders. Tell you the honest truth, the better way to do this is to go find, and this might be worth your while, go find a workable program in OpenGL like the one we did in my OpenGL class. And when we write shaders, we'll write them in OpenGL, compile them and debug them because it's quicker that way. Once you get the shader to work, then you can plop it into Vulkan and we don't have to go through all the debugging of this stuff, because now you're going to have to get used to the GLSL compiler and what error messages it's going to kick out. Gee, we barely know how to work OpenGL's error messages. So I tend to write my open the shaders in GLSL on an OpenGL program. And then if I want to move it to Vulkan, and I wait till I debug it on the OpenGL and then just move it over and it works first shot. It'll be great. However, we still have one problem. We have to compile the darn shaders. And I realized that you guys are not going to go to a command prompt and enjoy that. That will not be fun. And so you owe me for this one. Check this little file out that I wrote for you. This hurts me greatly to have to do this. And look, it's even blank. I can't believe it's blank. I thought for sure I made that work right. Hang on. Guess I'll have to post it. Ah, Fielder, you're an idiot. You know that? There it is. Here it is. Let's try that again. There we go. I'll post this on the website. I'm sorry. I thought I had that in your stuff. Obviously, that file was blank. Okay, so what I've created here is this is a batch file. Oh, that hurts my feelings to even say the word batch file. And forgive me for my little rant here. So I'm doing a little rant here. I'm even citing Umer. Oh, let's have a go. He's always so happy about things. Let's have a go and write it. Microsoft is just ridiculous. They make me crazy, but I wrote it anyway. And this is my mostly dead art, is writing batch files. But I wrote this little batch file here for us. So what you'll end up doing is in your program, this is how we'll do it. You're welcome. We won't be able to do it today because I screwed up. Shaders. What you'll do is you'll come over here, grab the vertex shader that you've checked, and just drop it on top of the batch file, and it will create the SPV file for you. You're welcome. And if you want a real exercise in, are you kidding me? Go read this and see if you can figure out what I'm doing. I can't believe Microsoft survived. I really can't. It's just ridiculous. That took me a long time to work that one out. How do you remove quotation marks from a variable? Yeah. Oh my goodness. Candide, I'm aware that they own the universe. I'm aware of that. What frustrates me is that this is some ugly, ugly stuff, and it's not very good, and they still own the universe. Obviously, you don't have to be talented to own the universe. Okay, enough of the shenanigans. So I'll show this to you guys later on when we start getting into the shaders, but it won't be too bad. I just wanted to show you. So what we're going to do here in the create graphics pipeline is I'm going to grab the name of the SPV file, which is, again, that's a binary file with the code already compiled in it. And then we're going to build up a shader module. So we'll build up a vertex shader module, pass it the code to that, and then we're going to get a vertex shader module, and then a fragment shader module, tessellation shader module, geometry shader module, if you so desired any of those things. All right. Then we need to come down here and tell it about the stages. What stages are we doing? Since we're not doing a tessellation shader and we're not doing a geometry shader, we need to let it know that we're just doing a vertex and a fragment one. And I love this. You even have to tell it that the entry point is called main. So we're going to set, so again, but this is just setting up that information. None of this information is done by the driver because there really is not much of a driver here. So we'll just set all these things up, all the data that needs to be set up. In terms of size, this is actually not very much. This is just a bunch of floats and integers and things, and just setting up stuff. So the size of this whole thing is really not very big. So again, that's just all data, all data, all data, all data. And then when you get down to here, VK create graphics pipeline. That's all it does. If you think back to the OpenGL days, we had a GL use program. And we would say something like GL use program 1, GL use program 2, or whatever we enumerated the programs to do. GL use program, that just swaps between already pre-built pipelines. So in OpenGL, what we were doing that we didn't have to deal with because OpenGL took care of it. When we created the shaders, it was actually creating, in real life, it was creating a whole pipeline. And then it just made a whole list of these pipelines. We're going to do the same thing in this class. We'll set up a bunch of pipelines, and then we'll just be able to swap. Hey, go use that pipeline, use that pipeline, use that pipeline. We just got to remember to kill it when we're done and get rid of them all. So here's just some cleanup information here. Sweet, no problem. Okay. Hey, we're really kicking some butt. How late does this class go today? I don't remember. 2:20. Holy smokes. Is that right?
Yeah. This was going to be the in-person, so I think scheduling had you for the 4 periods.
They can't do this for 4 periods. They'll die. Let me rephrase. I can't do this for 4 periods. I'm going to die. I tell you what, let's just finish this stuff off and I'll go contact Dina and find out somebody. That can't be right. I'm just looking at this now. 11 until 2:30. They'll die, Umer. We can't kill these guys. I like these people. Oh my gosh, until 2:20. Holy. All right, back to work. Okay. That just can't be right. Okay, I've now created a graphics pipeline. Cool. So rather than having shaders, we're going to be calling them pipelines from now on. So just a syntax change. Let's come over here and check this one out. This is a command pool. You'll like this guy. It's cool. Command pool. Let's go take a look. There's not much to see in here, but there's some things I'm going to have to discuss about how Vulkan operates. Makes me crazy, some of this stuff. Here we go. You ready? All right. What I'm going to want is a command buffer. A command buffer, if you recall in the OpenGL days, I would say load up your matrices, do this, turn on your texture, set all the, and then draw the triangles and all that business. I would say all of these commands, and they would all be in the render call. Well, what we're going to do from now on is we're going to put all the drawable stuff, all the commands to draw things and hook things all up. We're going to put them into what's called the command buffer. Okay, now Vulkan's going to do everything Vulkan way, which just seems like it has to be the most complex way possible, but there is logic behind it. In order to get a command buffer, you have to get a command buffer out of the command pool. Okay? So back when Umer was the program coordinator, he had a pool of teachers, and if you wanted a particular teacher, you would reach into the pool and grab a teacher out of the pool. You follow what I mean? So we've got to first go create a command pool. Now, one of the other advantages of a command pool is that we can put several command pools out there and pull command buffers out of each one of the different pools. And you might think, why would you want to do that? Aha, says Scott, because Vulkan wants to be very clever about things. What if I had multi-threading? Now so those of you who are taking Engine 5 class now might have a small idea of what I'm talking about. Let's say you've got a computer with multi-core on it. That would be pretty much all of you. If you had a multi-core machine, we could have multiple command pools on various cores, and then I could pull command buffers out of each one of those pools. You can't multi-thread. You can't multi-thread out of the same command pool. You can only multi-thread out of separate pools, or something along those lines. We're not going to do that in this course. That would kill you for sure. But that's the idea. We're going to have pools of things, and then you reach in and grab junk out of the pool. So that's what this create command buffer is, and that's why this one's the shortest one we've got here. It just says, hey, if your device supports it, go get a command pool. Here's the data about it. Go get it, okay? And a command pool is just going to be a buffer. It's going to be a container that we're going to put all the draw commands into, and then we're going to ship it down once. Now, again, I mentioned this earlier. Let me just say it again. Let's say you're playing a video game and you just sort of stand there and pause for a moment, And this thing is clicking along at 60 frames a second. Unless you update the command pool, I'm just going to draw what's in the command pool again. And I don't need to phone home to the CPU to do that. So the GPU can now draw it again, draw it again, draw it again, draw it again. It doesn't know. And if you want to change what you're drawing, if you want to change the projection matrix or change the model matrix or the view matrix, or you want to do anything different, well, then you're going to have to update the command pool, or sorry, the command buffer. We'll get to the buffer here in a moment. So we're going to set up all of that business, but first I've got to get the pool, or I got to generate the pool itself, and then later we'll go grab a command buffer out of that pool. But all this is so I can break the tie between the GPU and the CPU. So the command buffer is going to hold all those instructions. But to get the buffer, I got to have a pool. Gross. Okay. I don't want to talk about this one. This one's easy to deal with, but I think I'm burning you guys out. So, or at least I fear I'm burning you out. Depth resources. This is talking about the depth buffer and how deep that's going to be and setting up that kind of information. The frame buffer now. The frame buffer is actually what I'm drawing onto. So I'm going to want to go draw onto the frame buffer. This is the actual hardware that I'm going to be writing into. The swap chains were the virtualized version of what that frame buffer was. I took you to that web page that will talk about that in long wind if you want to read more about all that stuff. Also, the Vulkan tutorial that I gave you, the link to the Vulkan tutorial, will go into some great depth onto what the frame buffer versus what the swap chains are all about. From a virtual point of view, we just have to worry about the swap chains. So as we're thinking about things, we're thinking maybe swap chains, but ultimately we're going to have to create frame buffers and depth buffers and all that business. Remember, this is still just the initialization. This isn't running Vulkan. This is just setting things up. Fortunately, the machine operates at billions of instructions per second, so this doesn't take much time. Let's jump down to here now. Create texture image. Let's go take a look at that guy. Uh-oh. This one here is mutable. Another good C++ word. We can modify this one. And we'll be doing, one of our assignments will be to come in here and mess around with this thing. I'm going to go create a texture image. So in this one, I need to put Mario's pants on. So Mario's got his little, whatever, I forgot what I dressed him up as. But I've got Mario all dressed up with his fancy clothes, and that's coming from a texture. This thing down here is this is load image. That is an SDL command. So Kendi, maybe I did lie to you. This is an SDL command, but it's not linking in with Vulkan. This is just SDL on its own, loading up the image and putting it into an SDL surface. Now, I kind of like SDL surfaces. I don't know how GLFW really does it. I think it's along these lines, but I like the way that these guys do it. What the SDL surface contains is a couple of fields. One of them, W, yeah, go figure, width. The other one is height. And how big is this image? I'm going to assume that all images coming in are going to be PNGs. It's a lousy assumption to make, but, and look, it's the only comment I've made so far to remind myself, why did you do that? It's the format. I'm going to assume that everything we're reading is RGBA. And let's just do that. I don't feel like worrying about whether or not a JPEG comes in there. Go buy Photoshop and convert everything to PNGs. Your life will be better. Okay, now PNGs do RGBA, so I'm going to need to multiply it by 4. So I need 4 bytes for every pixel that I've got on this thing. Good grief. Dina is now trying to call me. I didn't even know Dina had my phone number. Oh, I'm in class, Dina. You set me up for 4 hours.
She gets the blame now for your schedule.
She's got a student that failed a class last year, and because he didn't submit some work, but he submitted it to her, and she's going to be a great program coordinator. I can just tell, because she has nagged me about this yesterday during class, and now today during class. She's going to be an excellent program coordinator. You got to get this figured out right now. No, I'm in class. He set me up for that. Let's get back to my texture image here. So I'm going to go load this up. I'm going to use SDL to load up the image. We'll get the, I'm going to allocate the amount of memory for it by finding out what the width and height of the image is, multiplying it by 4 for RGBA. And this just requires me real quick to talk about, just for a moment, another one of the wacko things that have to go on here. Recall that this is a separate piece of hardware. This is not connected to the GPU. This is sitting on the motherboard of your computer. This is a wholly different piece of hardware. So saying that I've got a pointer to a memory cell on the graphics card doesn't make much sense from the GPU's point of view. So I can't say that it's got a memory address that I can get at. However, there is a way of kind of doing it. And the way we do it in this world of Vulkan is we're going to have an area of memory on the GPU called staging memory. And in this area of staging memory, I can load junk into it from the CPU, close the link to that, and then tell it, move the stuff in the staging memory to where it really belongs in the GPU. The GPU is not going to let us play around with memory inside of it. We're not worthy. So all they're going to do is they're going to let us put some stuff into the staging area of memory, and then we're good to go. Okay. So that's what's going on here in line 700 already. My gosh, we're still just initializing, and we're 700 lines deep. All right. So I'm going to go get the type of memory I want as staging buffer memory, and it requires these sorts of things. Go look them up. I don't want to talk about them. It's nothing big. It's just talking about that we're going to be transferring memory from the CPU into the GPU, and you got to kind of set that up. I'm going to need to create the buffer. The next one here, hey, do you remember this guy? I love that. Void star. That means I don't care star. I don't even know what it points to, but it's a pointer. And what does it point to? Beats me. And what this call down here is going to do is going to say, hey, VK map memory. And I'm going to talk about the device. I want to map the memory to the staging memory. And it's going to be the image size, which I calculated up here. So it's got to be a block of memory in the staging area. That's going to be big enough to hold the image. And then over here, I'm going to pass you the address. Now read this carefully. Come on, you're C++ers now. It's a void star, so it's a pointer. Ampersand is a pointer to the pointer. So that's a void star I'm passing it. Okay, so this VK memory needs a void star. It needs a pointer to a pointer because I'm going to pass it the address of the pointer called data, and it's going to load into it a number. It's going to load in the address of the staging memory on the GPU into that pointer. So when I come back from this call, data will then contain the address on the memory card of the staging memory. Got it? Okay. Then I'm going to do... I just heard a whimper. Was that from Candide? Oh. Okay, then we're going to do a memcopy. Memcopy, check out memcopy. Let's see, let's go back up to here. My goodness, memcopy. This comes from the C days. This is some of the oldest, this is part of the C library. It's really old stuff. This is for copying chunks of memory. So if I have a big, large chunk of memory and I want to move it from one spot to another spot, you call memcopy. This is about as old as it gets. I think the first time I used memcopy was in the early 80s. That's how old this sucker is. And it's a really fast way of transferring information. And the call is really simple. It says the destination, this is where you want to put it. And this is the source of the data that you're doing. And this is a size _t. Remember I told you that counts things. and I'm going to pass it this much. Notice it's all doing void star stuff here. And the void star means it's just going to be doing it byte by byte by byte by byte. It has no idea if these are integers, floats, longs, doubles, no clue. It's just going to take them as a chunk of bytes and move them and put them into I don't even know. I love this call. So we're going to transfer all the pixels of the image into the staging buffer area of memory here based on this address. So here it is. This is the image. I had to pull some fancy stuff here because the image size up here, this image size was not the right type to handle or for memcopy to deal with. Memcopy was asking for a size T, and Vulkan wants it to be a VK device size. So I needed to drive a static cast to it to convert the VK device size into a size T variable, even though they're all the same anyway. They're all the same, but Microsoft isn't going to let me get away with it. So I had to go pull a static cast on it to make that work. Phew. So then I transfer all the information down, and now let's close the link. Be sure this happens. I'm going to close the link to the staging memory. In fact, I probably should have zeroed out the data value here. I probably should have set that back to null. Of course, it will get popped off the stack as soon as we're done. Okay, now inside here, now that I've got the image in the memory, I'm going to tell it that, hey, I've got it down in the staging area. Its width, its height. The format is going to be 8 bytes of red, green, blue, and alpha. And it's going to be in this order. That's what these keywords mean. You're welcome. I had to go look them all up. And you'll see that Vulkan does this stuff a lot. I'll promise you I will help you with all these things. Nobody can memorize VK image usage transfer DST bit. No one's going to remember that stuff. You have to look them up. Okay, and then copy the staging buffer to the actual image area. So now I'm going to take it out of the staging area and actually put it into the GPU. Well, it's in the GPU, but it's in the staging memory area of the I'm tired. This is tough stuff. We're going to have to stop here soon. Because I know you guys aren't following me here. I'm not following me. And again, I had to go do some static cast to convert this thing into a uint32, even though it really is one anyway. So, but I'm going to do a static cast just to make sure that Microsoft is happy with it. This is now loading the memory from the staging area into the actual image area of the graphics card. And we're done with that. And then at the very end here, we have to be nice to SDL. Remember, I created a surface? Way back there, I created a surface. So down here, be sure you free the surface or we have a memory leak. Whew. All right. I don't know about you all, but I'm cooking here. So I think we're probably getting close to being done for the day, and I probably should call Dina back. And let's just go back and look and see what else is being done up here. So we've got the create texture. So anytime I can make a whole bunch of textures and move them all into the GPU. We'll be doing this routine many times, and we'll be modifying that. So this one is one that we are going to mess around with. Let's see here, the graphics pipeline. That's another one that we're going to be messing around with. And then let's just go look at this last one here, and then we'll be done for today. I'll get to this stuff later on next week when we get all to this stuff. Okay, let me just tell you about these things here though real quick. Vertex buffer. The vertex buffer is kind of along the lines of what we've dealt with in the past. When I say the word vertex buffer, I'm going to be loading all the vertices into the memory of the GPU, and then I'm going to load up what's called an index buffer, and that's because we're going to do something that Umer loves. We're going to do a process called vertex deduplication, and the way that that programs like Blender or 3D Studio Max operate is that in their OBJ format that they create individual triangles. Now, if I have two triangles and the two triangles share an edge, they also share two vertices. Can you see that in your mind? If I had two triangles and they were touching each other, the two triangles would share an edge. If they share an edge, they also share vertices. In the OBJ format, they do not. In the OBJ format, I'm going to draw three vertices out, and then if this next triangle is associated with the first triangle, I'm going to draw three more, or I'm going to write out three more vertices, two of which are redundant. And that's just the way the OBJ format works for triangles. So we're going to go through a process here in class where I'm going to do this vertex deduplication. We're going to go in there and look for duplicate vertices, and then we're going to draw things a little different. We're only going to store the unique vertices, nothing more. So in the old days, in the OpenGL, we stored a whole bunch of redundant vertices, a ton of them. We just didn't worry about it because we had other things to worry about in those days. But now we're working on efficiency. So I'm just going to only store the vertices that are unique. But in doing that, I'm going to need a secondary buffer called an index buffer. And this index buffer is going to be the draw list, is another word for it. The draw list is saying, hey, take vertex 1, 2, and 3, draw those as a triangle. Then take 2, 3, and 4 and draw those as a triangle. And that's what's going to be inside the index buffer. Okay, the uniform buffers down here, these are the uniforms. We're used to the idea of some uniforms. You've dealt with that in the OpenGL world. The uniforms were the projection matrix, the view matrix, the model matrix, and all that. And I'm going to show you how to do it in a much slicker way than we did it before. We're going to make a camera, but then we're going to make a single camera that has a block of memory in the GPU, and every shader will be able to look at it without me having to update it. In the OpenGL way of doing things, if I had 10 shaders, I'd have to tell every shader what the projection matrix was doing, the model matrix, and all that business. I'd have to tell each one separately that this is what I'm doing. Aha, not anymore. Now we're just going to make a little tiny block of memory, call it the camera, and then all the subsequent shaders will reach back and just, oh, that's what the model matrix is doing, that's what the view matrix is doing, and that's what the projection matrix is doing. Ooh, that'll be clear. That'll be cool. So I'll show you how to go do that stuff coming up. And yeah, and then the rest of these things, don't worry about the descriptors yet. That's just complicated stuff. But as usual, in order to get a descriptor set, you had to pull it out of the descriptor pool. So I need a pool of those things to get the descriptor sets. And then the command buffers, that's just, hey, what's the darn draw list? What do you want me to do? Well, draw all the triangles using the vertex buffer and the index buffer. Let's look at that next week, though. Let me just show you this one last one here, because this one's going to be simple, and I know you'll be able to deal with it. Hey, it's TinyOBJ again. So I did load up TinyOBJ here, so if you pass me a file name, I'm going to go load up TinyOBJ and load up all of the shapes, the materials, and get the warnings and all that business. And then down in here is where we're going to be doing the vertex deduplication. And we'll deal with that later on. I just wanted to show you this one last little bit here. I'm going to go open up the file and go read the OBJ file, and we'll let TinyOBJ deal with that for us. Yay! Okay, with your blessings, I think we'll call that a day, don't you think? And then I'll check with Dina Umer and the scheduler and all that, and find out if they're really meant to have a 4-hour. Usually it's just a 3-hour or 3 section, or what is it, 3 periods for a class, right? Yeah. And yeah, so let's go find out what that's about. I don't know where the 4 came from. That may just be a boo-boo. Okay, groovy guys. So how about that? There's no homework this week. Just make sure everybody gets it up going. If anybody couldn't make it to class today, let them know how to get this up and going. All right. So there's the introduction to the initialization process of Vulkan. And there we go. We got Mario back up and running around. Notice Mario's not lit. This is just a texture mapped version of Mario, and we'll be making multiple lights. We'll be doing a lot of the stuff that we already wrote in OpenGL class. In fact, we're going to steal OpenGL class stuff. I'm not going to make you rewrite them. We'll just make sure that they work in Vulkan now. Any shader you write that works in Vulkan will automatically work in OpenGL. So this will be cool. All right. You guys have any questions? Anybody lost, confused, dazed, broken, anything?
Is it just me, or does Mario look a little brighter compared to when we did it in non-Vulkan?
He is a lot brighter than when we did it in the OpenGL version, because in the OpenGL version, what we were doing is we were lighting him. This is not lighting. This is just the texture map. Okay, so there's notice there's no shading on all of this. So nothing is going into shadow. So there's no Fong in this one. So one of our first projects will be to take the Fong from the OpenGL days and see if we can modify Vulkan a little bit. Part of my my thinking for today's class was just to show you the magnitude of the code we're playing around with. And I think this class is going to be fairly simple to deal with. The idea here is to go in and modify things a little bit, and the real task is just don't break it. Okay? And if you break it, then just start over.
Well, that sounds fun, just like in OpenGL.
Well, OpenGL, we could debug things a little bit, but because debugging is not really good in this thing, and because so much of it is things I keep telling you, don't touch this, don't change this, don't change that. We can change pipelines. I can change what object you're loading. I can change images. But for the most part, we're not going to want to change anything. If you accidentally change something, it blows up. It's going to be a real drag to figure out why. And Tyler can verify that one. It just says no. That fix that we were talking about earlier, he ran the program and it came up with the number of devices he had was 0, and then it just blew up. Oh, okay. How do you fix that? Apparently he was able to find that out, but I still don't even know if I understand it. Yeah, so this stuff is it's a little touchy, but I'll get you good at it. We'll get good at it, and then we can put something other than Mario up here. Okay. But this is going to be this will be a great thing to have in your toolkit for getting a job. Not a lot of people know about Vulkan, and the people who do don't like it. So if you can learn to appreciate it, that's a real great asset to your career in this. Every engineer I've talked to ever out there in the working world, you mention Vulkan and their eyes light up. Really, you know how to do that? You know how to do that? I had a request even from an engineer. This is Sean over at AMD. They're the makers of this thing. He goes, hey, when you finally work out a really good framework for Vulkan, can you give it to us? I said, you guys wrote it. I said, yeah, I know. I can't tell if that's a compliment or just a cop-out.
You know, Scott, that reminds me, I was watching a Vulkan talk at GDC.
Mm-hmm.
It was this year or last year. And I think at the end of the talk, the person giving the lecture hired any student in the room that knew Vulkan on the spot. It was incredible.
Be sure you tell Am that story. I want a new laptop.
Yeah, I'll have to dig up that video and show it to you, Nate.
Oh, very cool. Very cool. All right, I'm going to stop recording.